So for part A, what we're looking for, are these things part of the same family? And this question is going to extend because you can see in part B, we're going to go to our cube roots as well. Now, if we wanted to do the same activity that we did in cube roots, we need three-dimensional objects in order to work with it and get a little bit tricky. But the mathematics stays the same no matter what power root you have. You can only add or subtract radicals if they're part of the same family. So if you have 9 root 5s minus 5 root 5s, those are part of the same family. And you'd be left with 4 root 5s. That question is nice because the radicals were already written as mixed radicals, so you know what family members they belong to. Often, like questions B and C, they're not in their families yet. They're written as entire radicals. So we're going to have to simplify these. And the way that we simplify them is going back to our powers chart. Since these are cube roots, you're looking at your powers of 3. Remember that 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. And you're going to have to check, is there a perfect cube that divides 24? Well, the only one you'd have to check is the 8, right? Because all the other ones are bigger. 24 divided by 8? Yes, it does. So I can start by saying the cube root of 24 is the same as 8 times 3. The cube root of 192. I need to take out our calculator here. Does 192 divide by any of these? 192 divided by 64? Perfect. It's 3. So it's going to be 64 times 3. And 375 is 125 times 3. Now, the reason we're checking those numbers is because we know the cube root of 8. We know the cube root of 64, and we know the cube root of 125. So I can bring this out. The cube root of 8 is 2, and I would be left with the cube root of 3 inside. And this is a mixed radical, and it's telling me which family I'm dealing with here. The square root of 24 was part of the cube root of 3 family. 64, the cube root of 64 is 4, so that is also part of the cube root of 3 family. Cube root of 125 is 5. So all of these are part of the cube root family. So we have 2 of them here. Then we subtract 4 of them. Then we subtract 5 of them. If you did 2 minus 4 minus 5, you would get to minus 7. And that's how many of the cube root of 3 families would be left. Negative 7 of them. So again, the idea is we need to write them as mixed radicals so we find out what family they belong to, and then you're only able to add families that are the same together. Part C, just put that into more space here. Square root of 63. Now we're dealing with square roots, so you're looking at your perfect squares. Should I go back for a second? That's good. Anybody need me to go back? So you're looking for your perfect squares. Remember, 2 squared is 4. 9, 16, 25, 36, 49, and so on. Is there a perfect square that divides 63? 9. Because it's 9 times 7. What about 40? 4. 4 times 10. 90? 9 times 10. And 28? 4 times 7. So what's the square root of 9? It's 3. Square root of 63 is part of the square root of 7 family. It's 3 of them. Square root of 40 is part of the square root of 10 family. It's 2 of them. We had that on our diagram, right? We drew a square root of 10. You can imagine that length. You have 2 of those. Minus 3 square roots of 10 minus 2 square roots of 7. Now, what do I have? Do I have any that are the same family? Yes. 3 root 7s minus 2 root 7s will leave me with just 1 root 7. 2 root 10s minus 3 root 10s will leave me with negative 1 root 10. You can write the 1 out in front, or you can just write it as a negative root 10. There's our final answer. Don't keep going, because these are not alike. You can't put them together. This is as simplified as we can get for this question. Your homework questions you can do are numbers 3, 4, and 9 for this one. And just as far as a mind-boggling thing, think about square root of 10. You were able to draw square root of 10 on that centimeter paper by going over 3 and up 1 and connecting those, right? You just drew square root of 10. Now let's just think about what that means. If you type square root of 10 into your calculator, it gives you 3.16 dot, 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 and it's a number that continues forever. It's an irrational number. The decimals go on to infinity, and yet you can draw it exactly. Is that kind of abstract in your mind? It's a number that goes on forever as far as the decimals go, but it's just as easy to draw as, say, 2. You can draw a length of 2 just as well as you can draw the length of square root of 10, which is a decimal, which goes on forever. Isn't that just like mind-boggling kind of ideas happening here?